In the name of God, and welcome back to the endocrine physiology subject. As you remember, in this subject, we started to discuss about the endocrine system, how the endocrine system is working, what are the main principles that we have about the endocrine system, what is the concept of endocrine gland, what is the concept of hormone, how hormones are being regulated, how they effect are being generated by the hormone receptors. And then I started to discuss about the main endocrine gland in the body. However, I told you that the endocrine system cannot be limited to just these main endocrine glands. And I told you several times that there are lots of other cells that have endocrine function. But according to your curriculum, we limited ourselves to the main endocrine glands. And for the first part, I spoke to you about the hypothalamus and pituitary gland and the hormones that are released by this axis. Uh, then, in this part, that is the number six part that I am recording for you, I'm going to start another main endocrine gland, and this is thyroid gland. You know, thyroid gland is a tiny, very small gland that we have in the anterior surface of our neck. If I want you, if I want to show you the location, anatomical location of the and orientation of the thyroid gland in the anterior part uh, of the thoracic, you can see that we have the thyroid cartilage at this part, and thyroid gland is placed in the anterior part of this thoracic. And as you can see, this gland is the most superficial gland that we have in the body. This schematic figure show the orientation of a thyroid gland uh, in in the front side of the front side of the trachea, and you can see the right lobe, left lobe, and the isthmus that connect these two lobes together. Also, you can see the some cartilage that we have in the larynx, such as thyroid cartilage and in this area, and also the cricoid cartilage of the larynx. Another point that you can see is the very huge amount of blood circulation that we have in the thyroid gland, and this show how much how much the blood circulation of this thyroid is important and is huge when we compare to the very small size of thyroid gland. I can say that the blood flow to the thyroid gland is tens of times higher than the blood flow that we have in the muscles, and this show the importance of this thyroid gland. This figure show another schematic figure that show the trachea, the isthmus, the right lobe, left lobe of the thyroid gland, thyroid cartilage, and also the main blood vessel that we have around the thyroid gland. And if we cross the neck, you can see that the trachea is located at the center, and the thyroid gland at the uh, at the anterior part. Behind the trachea, we have the esophagus that is a part of the gastrointestinal system. When we have a microscopic look at the uh, texture of the thyroid gland, you can see that thyroid gland is formed of several, or I can say uh, thousand of follicles, that they are some spaces that are covered by some cells that are named as epithelial cells. In fact, these follicles that we have in the thyroid glands are spherical shapes that are covered by by a covering of the epithelial cell. These epithelial cells and the colloid space that we have inside these follicles are very dynamic. I mean that their size can change, and according to their activity. The blood flow can change according to their activity, and the stimulation that they receive from pituitary gland. This is showing the same concept, but in a schematic figure. And as you can see, we have the blood vessels, and as you can see, there are lots of blood vessels, also the cubital epithelial cell that cover the colloid space. And inside these follicles, we have as I told you, the colloid space that is filled with some the secretion of these cells. In fact, the secretion of the cells are being accumulated in these colloid spaces, and this is the place that the thyroid hormones, firstly, when they are produced, are firstly stored in this colloid space, and every time that it is needed, these will be uptaken by the cells and then released into the bloodstream. When we are talking about the thyroid hormone synthesis in the thyroid gland, one of the most important characteristics that we have about the thyroid hormone is the iodide ion that we have and we need for the production of the thyroid hormone. In fact, thyroid hormones are produced by incorporation of iodide ions into one amino acid named as tyrosine. Therefore, the iodide balance is very important. If I want to show you the iodide balance in everyday life, you can see that from our food intake, from the different sources of our food, we have about 400 microgram of iodide that we intake every day. And this 400 microgram, that is, you know that it is less than half a milligram. Just 80 microgram is being absorbed into the blood, and the other, absorbed in the thyroid gland, and the other 320 microgram will be excreted by the kidney into the urine. Therefore, I can say that just 80 microgram is absorbed into the thyroid gland. And from this 80 microgram, as you can see, just 60 microgram is converted into thyroid hormones, incorporated into thyroid hormones, and another 20 microgram is again escaped from thyroid gland and then excreted into the urine. That 60 microgram of iodide that is incorporated into the hormones will be distributed in the form of thyroid hormones in different tissues. And then the thyroid hormone will be metabolized, and the iodide will then be excreted into the urine and some into the stool. Therefore, as you can see, every day we lost about 400 microgram of iodide and gain for the same amount from our food. And this is the balance that we have between our food intake and excretion. You know that in some situation that we need more iodide, this balance may change and less iodide is being excreted from the urine and the stool. And in situation that the iodide intake is increasing, then the amount of the excretion also will increase. From the early life, the iodide is being concentrated and stored in the thyroid gland. And if I want to tell you, we have about 7,500 microgram of iodide that is stored in the thyroid gland. when I'm talking about the iodide balance, it means that we have this storage, and this storage play role as a buffer, that every time that intake is decreasing, this content will help out, and every time that the intake is increasing, this is also another buffer state that provide us enough support for the iodide that we need for the production of the thyroid hormones. You can see that 70 to 80 microgram of iodide, 1% of the total, is released every day as thyroid hormones or free iodide. Therefore, you can understand that if we stop iodide intake at all, several days should pass until the time that we show the signs of iodide deficiency, because we have this amount of storage in our body. Except thyroid gland, that is the most important part of the body that concentrate iodide, but we have some other glands, some other cells that are able to uptake iodide from the blood, for such as salivary gland, gastric gland, lacrimal gland, mammary gland, and also choroid plexus. These cells are also able to uptake iodide, and you know that the uptake of iodide is a complicated process, and not all the cells are able to do so. If I want to show you in the thyroid gland cells, you can see that iodide uptake it is taking place through a secondary active mechanism. Have a look at the basolateral membrane. Sodium and potassium are exchanged, and the sodium concentrate by the sodium potassium ATPase pump. This use energy. Therefore, the sodium concentration inside the cell is low. Then sodium use its gradient, its chemical gradient, to enter the cell, and by using a symporter named as sodium iodide symporter, not only sodium enter the cell, but also one iodide ion also enter the cell in a secondary active mechanism. Then this iodide will enter the cell, and on the other side of the cell, this iodide will be exchanged with color. This iodide will enter the colloid space, inside the colloid space. Inside the colloid space, with the function of peroxidase, this iodide will be added to the tyrosine amino acid of a large protein named as thyroglobulin that is produced by the same cells. Therefore, we have a large protein that contains several tyrosine residual amino acid, and the iodide are added to this tyrosine amino acid. According to the state that if just one iodide is added to tyrosine, therefore we have monoiodotyrosine. If two position of the tyrosine is iodinated by the peroxidase enzymes, then we have diiodotyrosine. And now the production of hormones is very easy. If one monoiodotyrosine is added to one diiodotyrosine, then T3 will form. If two pieces of tyrosine that are diiodotyrosine are added together, therefore T4 will form. These proteins contain the hormone, but the hormone is not released until the time that a stimulus reaches the cell, and then the cell will uptake this protein into the cell. Inside the cell, you can see that under the function of the protease enzymes, T3 and T4 will be released from the protein and will be released into the blood circulation. Some diiodotyrosine, some monoiodotyrosine also will be released, that will be recycled, and iodide will be reused again, and this process will happen again and again. As I told you, the process of iodide uptake is being taking place by a symporter named as sodium iodide symporter. That this symporter is extremely important. Um, as I told you, except to the thyroid gland, that this symporter is being expressed in high quantity, but the same symporter also is found in the placenta. You know, it is responsible for uptaking iodide for the embryonic development and for delivering this iodide to the fetus. On the other hand, I told you salivary gland and lactating breast are also able to uptake, express sodium iodide symporter, and therefore provide iodide for the infant that is feeding with breast or breastfeeding is breastfeeding. The expression of this importer is not constant. Therefore, we can say that expression of this importer is changing. Different items, different factors are affecting the expression. For example, iodide itself is a regulator for this expression of NIS or symporter. The TSH, a stimulator hormone that is released by pituitary gland, is regulator for this symporter. Cytokines are also stimulating this symporter expression, and its activity is also regulated by these factors. Collectively, I can say that every time that thyroid gland is being stimulated, just the production or release of thyroid hormone is not stimulated, but also from the beginning, the process is being stimulated. And this is the expression of the symporter, uptake of iodide, then incorporation of iodide into the tyrosine amino acid, and then in the release of the hormone. This symporter could be inhibited by some drugs and some toxins, such as the pertechnate or perchlorate or thiocyanate. That you know that these are the toxins that are found in the agricultural system, and therefore it may bring about the different stage of the hypothyroidism in the patients. These drugs also can be used to induce experimental model of the hypothyroidism. Another enzyme that I showed you in that figure was the tyrosine thyroid peroxidase enzyme, TPO. This enzyme was responsible for incorporating the iodide into the tyrosine. Therefore, it is extremely important for us. This enzyme is located in the cell membrane of the epithelial cells. And if we block this peroxidase, it can block the production of thyroid hormones. It's the drugs that inhibit this peroxidase are inducing hypothyroidism, and as I told you, it catalyzes the organification of the enzyme of the tyrosine residue. This figure show this peroxidase function that add the iodide to the tyrosine and produce monoiodothyronine or diiodothyronine. And as I told you, the inflammatory cytokine iodide TSH affect NIS, and but for the tyrosine hydroxylase, also we have some drugs such as propylthiouracil that inhibit this enzyme, metimazole, anti-TPO, and antibodies. These are used as drugs for the patient that have different stage of hyperthyroidism. When this figure show the different stage of thyroid hormone synthesis. Firstly, you see that iodide is being reduced and ready to be added to tyrosine. We have two site for tyrosine addition. One is here and one is this position. Therefore, if tyrosine is added to iodine is added to a tyrosine, then we have monoiodotyrosine. Just there is one iodine. Here, two positions are iodinated. Therefore, we have diiodotyrosine. If one diiodotyrosine with attached with another diiodotyrosine, therefore tyrosine, therefore we will have T4, thyroxine or T4. As you can see, four positions are iodinated. And if just one diiodotyrosine is added to one monoaminotyrosine, T3 will be formed. Normally, the most abundant hormone or the most frequent form of hormone that is released from thyroid gland is in the form of T4. And T4, even though that we know that T4 is active, but its activity is far less than the T3. What will happen then? This T4 function as a prohormone. In the peripheral tissues, such as muscle, such as nervous system, skin, and elsewhere, there are one enzyme that is expressed in this cell, and this is named as deiodinase type 1 or 2. These two types of the iodinase are responsible for removing iodide from the tyrosine amino acid. Therefore, in the outer ring. Therefore, if the T4 is deiodinated in the outer ring, therefore the T3 will form. And T3 is, as I told you, is much more stronger and more active than T4. But there is another deiodinase that it is type 3, and I showed you in red highlight. And this type of deiodinase is, on the other hand, is working to inactivate T4 and convert the T4 into inactive reverse T3. As you can see, in the reverse T3, inner ring will be deiodinated, while the T3, the outer ring, is being deiodinated. Just the position of iodide removal determine if the hormone T4 is converted into T3 that is more active, or reverse T3 that is completely inactive. This figure shows the expression of the iodinase 1 and 2. These two enzymes are activating enzymes, and as you see, the iodinase type 1 is expressed in liver, kidney, skeletal muscle, but type 2 is expressed mainly in the central nervous system and glia. Also in the thyrotropes, of the pituitary gland. You can understand what I'm going to say. In the pituitary gland, this enzyme is expressed. Therefore, when T4 reaches the pituitary gland, it will be converted into T3, and T3 is stronger and it's able to inhibit this pathway and the activation of the T3 and in the feedback, negative feedback. And these enzymes, for example, when we have a patient that the thyroid hormone is increasing, these enzymes are decreasing to protect the cell against high level of thyroid hormones. And this is one way that to up to one level, if we exposed to high level of thyroid hormone, body will not be affected. Do you know why? Because the iodinase will be inhibited and less T4 will be converted into T3. Instead, more will be converted into reverse T3. The iodinase type 3 that inactivate T4 into reverse T3 is also, as I told you, is increased during hyperthyroidism as a mechanism, protective mechanism against hyperthyroidism. This enzyme also is expressed in the placenta, therefore protect the fetus from elevated maternal T thyroid hormones. We have also one intrathyroidal deiodinase that you remember I told you that sometimes some monoiodotyrosine and deiodotyrosine that are not uh, incorporated into each other and do not form thyroid hormones will be released inside the cell. What will happen to them? We have intrathyroidal deiodinase that remove the iodide from these interthyroidal from these mono MIT or DIT, and therefore the iodide can be recycled again and again. This figure, this table, show the different type of iodinase, type 1 and type 2 that are activatory, and type 3 that is inactivatory enzyme, and the location that they are expressed and the function that they have. Please review this table. Now that we talked some principle about the thyroid hormone, let's talk about the storage and secretion of thyroid hormones, and also the transfer of the thyroid hormone inside the blood. In this figure, you can see the colloid lumens of the thyroid gland, and when these cells are activated, you can see that the colloid endocytic vesicle are increased. It shows that more and more content are being uptake to release the hormones, and it shows the activation of these cells. Normally, every day we have the production of about 90 microgram of T4 and 35 microgram of T3 and another 35 microgram of reverse T3. This is the daily production that we have in the body. But as you can see, 100% all the T4 that is formed in the body is from thyroid gland. But from the 35 microgram of T3 that is formed every day, just 25% is from thyroid gland. The remaining 75% remaining is formed from T4. The conversion of T4 will produce them. For reverse T3, just 5% of the reverse T3 is released from thyroid gland. Another 95% is the production of conversion from the T4. The extracellular pool of this hormone is also very interesting. As you can see, the main storage form of thyroid hormone is T4. There is about 750 microgram. I can say that about 10 days, equal to 10 days of production of T4 is stored in the extracellular pool, and 40 microgram as T3 and reverse T3. In the plasma, the total T4 that we have is just 8 microgram per deciliter. And this, from this, just 2 nanogram is in the form of free. It shows that the remaining is bound to the transporting proteins, and half-life of the T4 is about 7 days. Do you know why? Because in the blood circulation, these T4s are connected to the proteins, and therefore they are protected against the metabolizing enzyme. For reverse T3, the free form of the reverse for T3 and reverse T3, the free form is much higher, and on the other hand, the half-life is shorter. What are the protein transporters? I told you that when the thyroid hormone are secreted into the blood, they are not able to solve in the blood. Therefore, they need transporter. And as you can see, 70% of the thyroid hormone are attached to a protein named as thyroxine binding globulin. About 10 to 15 another protein that is named as transthyretin, 20% to albumin, and just 3% to some protein named as lipoproteins. Therefore, we have a combination, we have a cocktail of protein that are responsible for transporting the thyroid hormone in the blood, and also provide a storage site for the thyroid hormones. And thyroid metabolism could take place in several steps. When T4 converted into reverse T3, it is inactivation. But if it converted to T3 could be converted into T2, and it is against inactivation. And sometimes, according to this sequential deiodination, we have deiodinated form of the tyrosine that is T0. This figure summarizes the metabolism of thyroid hormones, and as you see, sometimes they are deiodinated and form different reverse T3 or T3, but there are some other ways, such as sulfation, glycoronidation, ether bond cleavage, oxidation deamination, and by each of these mechanisms, thyroid hormone is removed from the body. And because the hormone is connected to protein inside the body, inside the blood, therefore they do not allow sudden increase in the blood circulation. They play a role as a buffer that absorb the hormone to the proteins and release them gradually and slowly. For this reason, this is showing the one experiment that the onset of the thyroid hormone action is very slow, but the duration is very long. Have a look at this figure. If we inject thyroxine into the body of one animal, it takes 10 days to reach the highest function, highest basal metabolic rate, as an indicator of thyroid hormone function. And then it takes about 40 days, another 30 days, to calm down and to remove the effect of this thyroxine. This clearly shows that the speed of the thyroid hormone action is slow, but the duration is high, and this is because of the presence of transporting proteins that I told you about in some slide before. Now, until now, I told you about the basic metabolism, the production, and the secretion and transport of the thyroid hormone inside the blood. From now, I will start to discuss about physiological effect of thyroid hormones. And because the file, I do not want to file length to be very long, and therefore I will stop here in this part, and the remaining of this physiological effect will be discussed in the next file. See you in the next file about the physiological effect of the thyroid hormones. For now, bye.